Okay, so last time we learned a new test, we talked about comparing counts of a categorical variable to what we think should be true, or what is the theoretical claim of the truth, and used our chi-squared test to decide if our counts were unusually far away from what's expected or not. Today we're going to be looking at sort of the same idea. We're going to be doing a couple more chi-squared tests, but looking at different types of data and what sorts of conclusions we can draw from those. So on your screen now, you're going to see a chart that I drew, and it's got sort of like one population, and we're looking at two different things about it. So I'm looking at one population of college students, but they all go to different colleges within the university. So in the first column, you see agriculture students, then arts and science students, engineering students, and social science students. And we're kind of looking at each of those different groups. How many of them post-graduation are employed, how many go to grad school, and how many are in other things after they graduate, other situations. And what we're going to kind of look at are the plans of students the same in those different colleges, relatively. And so now we're looking at proportions of different groups within the population of people. So we can't really just compare two proportions. We're looking at the proportions of all of these different groups and wanting to look at, are they homogeneous across the spectrum? So that's going to bring us to the chi-square test for homogeneity. And we're going to be looking at the proportions of agriculture, arts and science, engineering, and social science all the same. So I'm looking at each of those columns, and we're going to do some work with that. Okay, so with that introduction in mind, will you grab your note packets out, please, and open up to page 3. It should look kind of like this at the top. And so we're looking at Chapter 26, Day 2, where we're going to look at two different chi-square tests, one for homogeneity and one for independence. Okay, so we're just going to kind of read through. If you need to pause for a second to get that packet out, go ahead and pause, and then just resume when you're ready. So it says, to compare two proportions, we would use a two proportion z-test, look at the differences between them, and then kind of compare how they relate to each other. However, if we want to compare three or more proportions, like in the example at the beginning, we need a new procedure. And so the first step in the overall test for comparing several proportions is to arrange the data in a two-way table. And that's what you saw on that first screen, was a two-way table comparing two different groups or two different sets of categories, and more than two proportions in this case. Okay, and so we're going to think of the counts as elements of a matrix with R rows and C columns. In fact, if you want to grab your calculator out, when we get to our first example, we're actually going to be entering a matrix into your calculator. So if you are unfamiliar with how to do that, you probably learned how back in Algebra 2, potentially even used it again in pre-calc. So I'm hoping that you remember how to enter those matrices. If not, I'll try as best I can to walk you through it verbally. But there are going to be notes as well in the textbook on page 638. So if you want to grab a textbook as well to maybe share with your neighbor as you watch this video, you can do that, and that should help you kind of walk through. There's screenshots of your calculator screen. So I'll walk you through it verbally, but if that's not making sense, then go to page 638 of the textbook. Okay, tangent over. So we're looking at matrices, and you're just going to take the counts in the matrix, it counts in the table, essentially, that you're looking at, and put them into the matrice of your calculator. And so a matrix that has R rows and C columns is an R by C table with R times C cells. So a 2 by 3 matrix would have 6 cells in it, 3 times 2. Okay. Our null hypothesis as we do a test for homogeneity is that there is no difference among the proportions. So in the example on the first screen, we'd be saying that the proportions of students that go to employment or grad school or other are the same for all 4 of those colleges. That's what we'd be kind of examining. That would be our null hypothesis, and the alternative hypothesis is interesting land, where there is a difference among the proportions. Okay, so we're going to use the chi-square test to measure how far, again, this is going to feel similar to what we learned on Monday. We're going to use the chi-square test to measure how far the observed values are from the expected values. Now to do that, you're going to have to figure out what the expected values would be for each individual cell in the table. And we'll walk through that for a specific example or two in a minute. But the general formula is to find the expected counts for any cell. You're going to take the row total times the column total and divide it by the table total. And I'll kind of explain it has to do with the null hypothesis, because in the null it's almost like pooling. We're assuming that all of the proportions are equal, and so this formula helps us to get the number that would be there if all of the groups had the same proportion. And I'll kind of walk you through that one more time once we get to an actual example of numbers. Then you're going to need the test statistic, and we find the test statistic the same exact way for this test as we did for the goodness of fit test on Monday. So you just are going to use your calculator to run the test for you. Now today, all of you, even those of you with sad TI-83s, get to run the test on your calculator, which is awesome. And because otherwise it takes kind of a fair amount of calculations. We're not going to use our lists today. We're going to use matrices, and so it becomes kind of a pain in the butt. So the test is going to be able to be run for you on your actual calculator in the stat test menu. So that'll be nice. But the test statistic is calculated the same way, where we take the sum of the observed minus expected squared divided by the expected in each cell of the table. And then we just add all those up. That's what that summation symbol tells us to do. Okay? So there's a lot of information for you. We're going to add just a smidge more, and then we're going to do an example. So the degrees of freedom for a homogeneity, that's a hard word for me to say, and eventually the independence chi-squared test is going to be, we're looking at how much freedom do we have for decisions to pick in both our rows and our columns. So if we're assuming that the proportion is the same for each of our groups, and we have a total that we have to get to, once you say you have 3 columns, once you make a decision for the first 2 columns, the third one is kind of locked in place based on those 2, because we have a total that we're shooting for. And so that's where this degrees of freedom comes from. You really get R minus 1 decisions for your rows and C minus 1 decisions for your columns, because in both the rows and the columns, that last cell is locked in place based on what you quote unquote picked in the first 2. Okay, so that's where that degrees of freedom comes from. And the p-value is the area to the right of the chi-squared statistic under the chi-square density curve. Okay, and that's the same thing that we did on Monday. So first example is going to be a homogeneity test. Because we're looking at these 3 groups, and we'll kind of see the difference between that and independent in just a minute. But let's just read through this. Example 1. Medical researchers enlisted 90 subjects for an experiment comparing treatments for depression. The subjects were randomly divided into 3 groups and given pills to take for a period of 3 months. Unknown to them, one group received a placebo, the second group the natural remedy St. John's wort, and the third group the prescription drug Postrex. After 6 months, psychologists and physicians, who did not know which treatment each person had received, evaluated the subjects to see if their depression had returned. So I'm looking at these 3 different treatments in each column, 1, 2, 3, and we're then evaluating with each of those 3 treatments, did their depression return, or if there was no sign of it. Okay, and so again, we're looking at, are those proportions of depression returning or not the same for the 3 treatments? Okay, so the first thing I want you to do on these tables is find some totals. Okay, so I did my row totals of 60 and 30, and then my column totals were all 30. So we had 3 equal sized groups. Now, the reason that formula, so say I want to find the expected value for the depression returning on the placebo. Okay, depression returning here, the total proportion is 60 out of 90, so 2/3 of my patients, their depression returned. And my null hypothesis, what we're assuming to be true, is that that proportion is equal for all 3 treatments. So that means that we would expect, with the null being true, that all of these would have 2/3 returning and 1/3 not returning. And so that's the assumption we run through. So I like to think of it actually as 60 divided by 90 and then times 30 for the placebo group. Okay, that's the same thing as if I just do 30 times 60 divided by 90, but that's where that comes from. It's because we're assuming that each of those groups have 2/3 depression returning and 1/3 not. So if I do 60 times 30, multiplying these two, row total times the column total, and then divide by 90, I'm going to get an expected value of 20 for the placebo depression returning group. And then doing that same exact calculation all the way across my table, I get 20s all the way across the top and 10s all the way across the bottom. And again, that's assuming that all of my proportions are the same. Those numbers are only the same on the top and the bottom because we had equal size groups, 30 in each group. Otherwise, they won't always necessarily be the same counts. Okay? Now, once I have all of that information, all I want you to put into your calculator at this point is if you go to the matrix menu on your calculator, it's on the top left, so do that, and then hit edit on matrix A, and you're going to be entering a 2 by 3 matrix. So across the top where it gives you the dimensions, you need to do 2 by 3, that's row by column. And all you need to enter in is the observed matrix. So 24, 22, 14 in the top row, and 6, 8, and 16 in the second row. Then you can quit out of that matrix menu. Okay? And we don't even need to do the expected one because your calculator will do the expected one for you. So a lot of the times you're not going to need to calculate these expecteds except to make sure that all of our assumptions are met. We'll go through assumptions in just a minute. They're the same as what we did on Monday, assumption-wise. Okay, so let's start running this test. So we can skip the parameter step again. There isn't a defined mean proportion we're looking at here since we're examining a bunch of different proportions at one time. So our hypothesis for our null is that there is no difference in the recurrence rates of depression for these 3 different treatments. So there's no difference in the proportions of recurrence rates of depression. Alternatively, our alternative hypothesis is that there is a difference. Okay, so that there is a difference for some of the treatments. Okay, if we see a big difference, then we'll note that. Okay, we've got some assumptions that we have to check for. So the first assumption is I know I'm looking at a chi-squared test for homogeneity. If I have a two-way table, I have to have independent and random expected values. We have independent and random data. Okay, so it says that the groups were randomly divided, and they're independent of each other because they're not knowing if they're getting the placebo or the prescription drug or the natural remedy. Okay, and then all of your expected values, again, should be greater than 5, and they are. We've got 20s and 10s. So those are the assumptions I'm checking for. Okay, when all of that is met, and I'm looking at are those proportions the same across, then I know that I'm doing a chi-square test for homogeneity. Then I'm going to calculate my degrees of freedom. So R minus 1 is 1, because I have 2 minus 1 rows, and then 3 minus 1 columns. So my degrees of freedom is just 1 times 2. I've got 2 degrees of freedom. Okay? Now, at this point, we need to calculate our chi-squared, or test statistic. We're going to do that just by letting the calculator run the test for us. So you should already have the matrix in your calculator, and you're going to go to Stat and over to Test, and then find the one that says chi-squared test. So if you have an 84, you do not want the goodness of fit test, you just want the chi-squared test. Tell it that your observed values are in the A matrix, and then it's going to say something, I think, about how the expected values are going to go in B. Okay, that's fine. Give it your degrees of freedom of 2, and then run that test. Okay, when you run the test, you should see a chi-square value of 8.4. And when you run the test, you'll see chi-squared, you'll see P, and you'll see degrees of freedom. Okay, so your p-value, I want you to write it like this. The probability of chi-squared degrees of freedom 2 is greater than 8.4. And you should see there a p-value of 0.015. Okay? With a p-value at that level, again, I usually use 0.05 as my cutoff, but you can kind of decide what you want to do as long as you're consistent. Is I'm going to reject the null. So my making a decision is that I reject the null, and then my stating conclusion is we have a small p-value, so we reject the null. There is evidence of a difference in the recurrence of depression for the different treatments. Okay, we're done with that. Now let's talk through the other type of chi-squared test that you might see, and that's going to be a chi-squared test for independence. Okay, so let's read through this problem. It says, are handedness and eye color independent? So now you're looking at two different variables. You're looking at left-handedness and right-handedness versus eye color. And I want to know, basically, I'm asking, do those two things have an effect on each other? So it's a little bit different here. Instead of looking at one group, I'm looking now at two different variables. Okay, so I'm looking at two different traits. And I want to know, are those two traits independent of each other? So it says a random sample of 114 adults was taken, yielding the following data. Perform an appropriate test. So the first thing I did on here was I took all my totals and added them up. You're going to start to see me now look at those expected values to make sure they're all greater than 5, and you're going to see something kind of unfortunate happen. So the first one, again, I do 19 times 42 divided by 114. Assuming that the proportions are the same. And so you're going to see here, I start to do this, and then I realize here at the green eyes left-handed, I have an expected value of 3.8. So at this point, you kind of have two options, okay? Option number one is you can say, all right, well, my expected value is less than 5, so continue the test, but be careful, do it with caution. Your second choice is that you can decide to group some of your smaller populations together. So what I decided to do here was erase that and put green within my other category. So I've got brown, blue, and basically other eye colors, and I didn't make green its own category. So I combined those to be 6 and 33 as my total, and then I used that to be my expected value. So I did this total of these two times this total of these two, and then divided by 114, okay? And that gave me my expected value of 6.5 and 32.5. And now those are all greater than 5, so that puts me in a good spot. Okay, when I'm testing for independence of those two different traits, my null hypothesis is going to be that the handedness and eye color are independent of each other. That's boring. That would be boring. My alternative hypothesis is that there is an association between handedness and eye color. Okay, so if I'm left-handed, I'm more likely to be blue-eyed. Like, knowing something about your handedness would tell me something about eye color. Okay? My assumptions, again, I have to check for our sample represents adults, and it says they were randomly chosen, so that's good, a random sample, and they're independent. My sample of adults, the adults, their handedness and eye color are independent of each other. That's what that means. We have counts that so we're looking at counted data, and all expected counts are greater than 5. Because of this, I'm doing a chi-square test for independence. Again, I've got now, because I combined these two categories, essentially now I have 3 columns and 2 rows. Sorry, 3 rows and 2 columns. Got that backwards. So my degrees of freedom is 2 times 1. Okay, so go back to your matrix menu. Get rid of your old matrix. Now you're going to do 3 by 2 matrix. Okay, with 6, 36, 7, 28, 6, and 33 as your entries in that matrix, that 3 by 2 rows by columns. Then go ahead, go to stat tests, and run your chi-square test with matrix A. And take a look at that chi-squared, that p-value, and the degrees of freedom to make sure everything is making sense. If you need to pause quick to do all that calculator work, go ahead and pause and then restart. And you should have gotten a chi-squared of 0.71. Then your p-value is the probability that chi-squared with degrees of freedom 2 is greater than 0.71. And that's a p-value of 70% or 0.7. So with this large p-value, you have to fail to reject that null. There's not sufficient evidence of an association between eye color and handedness, which makes sense. I don't think I've ever heard anybody say that right-handed, you're more likely to be blue-eyed or anything like that. That makes logical sense to me, that there's not an association between those. Okay? Cool? Good. Let's finish up those notes and talk about when to use which of the chi-squared tests. So, you use a chi-squared test of goodness of fit when you want to show that the distribution of counts in one categorical variable matches the distribution predicted by a model. Okay? So, one categorical variable and a one-way table. And so an example of that was when we were comparing the counts of a bag of M&Ms versus what the website theoretically said there should be. So when you're specifically comparing a set of data to a theoretical idea of what the data should look like, that's going to be goodness of fit. How well does our data fit the model? Okay? You're going to use a chi-squared test for homogeneity when you want to show that the distribution of counts for two or more groups is the same. So one variable that you're looking at and a two-way table. One variable with two or more populations. Okay? The distribution of X is the same as the distribution of Y. So again, when I was looking at the distribution of those different colleges, okay, and I was just looking at their plans for after graduation, different groups of people, okay, but only comparing one thing. A chi-squared test for independence is when you want to show that two categorical variables are independent for one group of individuals. Okay, so instead of one variable, now I've got two variables, looking at that two-way table, and I'm just looking at one population, but comparing two traits. So eye color versus handedness. Or another example would be the book gives an example of talking about the rates of people getting hepatitis C versus people having tattoos. Okay, so comparing that one population, but is getting a tattoo independent of getting hepatitis C. Okay, there might be an association there, maybe. Okay, and so those are kind of the three different things that are happening. From here, there should be a worksheet that the sub has, so go through that worksheet. I posted the answers both on Classroom, and if you follow that QR code on the worksheet, it should take you to solutions as well. So check your work as you go. And I'm hoping that this all makes sense. If not, feel free to shoot me an email. I might be able to respond while I'm at the district office today. Or then I'll know for sure that we need to kind of revisit some of this stuff tomorrow when I'm back. Okay? Good luck with your worksheet. I will see you all tomorrow.